Well, thank you for being here because we have Barbie and it's also lunchtime. So we are really make our best to make it worth it. And nothing better to start our session than a little challenge. So, looking at this chart, what would you say about the relationship between X and Y? They look very similar. Maybe it's a good idea to use one to predict others. Any thoughts about it? And if I tell you that the correlation between X and Y is about 67%, would it change your thoughts about it? Would it be a good idea to use X to predict Y? Maybe Miguel has something to say about it. They cut Miguel.
I don't think that will be a good idea since we don't know what these curves are about.
Well, Miguel is a specialist that don't fall into data traps. So maybe, just maybe, we should listen to him and look for more information. And well, the X is Nicolas Cage movies and the Y are death by drawing. So we are humans, and we know that there's no possible way that the number of Nicolas Cage movies can impact on the number of deaths by drawing. Of course, this is a funny and obvious example, but in our life, there are many situations where it's not so obviously that doesn't make any sense to use one variable to explain other. And the models are not humans, at least for now. And if you put this in the traditional model, he will learn association between these two variables. So it's very important to look beyond data. We can't rely our conclusions, only look at data. And this is one of the main lessons we learn. We all know that, but in our daily life, many times we look just at data. We don't look at business expertise, we don't look at how the data was collected, and sometimes we don't even control the process of the data. The missing values, like yesterday we heard in the last talk, so it's really, really important, and this is one lesson we would like you to take home. Look beyond data. So, and now we can say one of the most famous statements on causal theory, correlation is not causation. And although this statement is true and it's very important, we should also not ignore completely correlation. It's a good metric. It's important in data analysis, but it needs a context like all other things. And we must listen to our common sense because we are humans, we have common sense, and we have previous knowledge that can help us decide if one thing makes sense or not. And Julia Pearl, who is a reference in the causality theory, made the ladder of causality, which formalized very well this idea about the difference between the humans and the causality. So when you look at the ladder of causality, the first step of the ladder is about association. The models we are most used to, like the supervised and unsupervised machine learning models, and also traditional statistical models, are in this stage. They learn from the association. Like in the example we saw, if we put those two variables in the model, he will predict one with another with no problem. And you would have good metrics because there is an association. It doesn't make sense, but there is. The correlation in that case was just a coincidence, but it was there. Animals also learn by association, and so they are in this stage. The second one is about intervention. Okay? Intervention is the first humans were in this stage, and they started interacting with the environment, changing some things, and observe the effect of that changes. If we think in an example with aspirin and headache, in the first stage we would say a lot of people that take aspirin have headaches, and one thing must be related to the other. On the other hand, in the intervention state, we would say something more like, what if I take the aspirin? Will my headache be cured? There's already a cause and effect question. But in the last stage, where we are, the humans, we call counterfactuals. And what are counterfactuals? are the ability to imagine a scenario that never happened. This is a human capability, and only humans can do so. We can think, following our example, one thing more like, was it the aspirin that stopped my headache? We start wondering if that thing didn't happen, what would be the result? And we need structural causal models to deal with this kind of complexity. Well, now that you know a lot, all of you are specialists in causality after this good information, let's get back to the marketing world and see how these things can help us. And let's start by thinking together in how can we evaluate a marketing campaign. When we have a marketing, how can we say if it is good or bad? We can think if the campaign increased our success rate, and here success can be anything you like. It can be, did it retain more clients? Did it sell more? Or did we increase the use of our app? It can be anything you need to measure. You can think if you had a high return on investment, or you can define any other KPI with the business or the stakeholders, and then look what happened. But now that you are specialists in causality, you may be starting to wonder, what if there is no campaign? Would I have the same results? Was it the campaign that caused that increase? And you can go even farther and think, is it worth it? Was that the best campaign I could do? Or could I make anything different to get a better performance? Let's try to answer together to these two questions in our presentation. And to start, let me show you how usually it's a more traditional way to look into the marketing campaigns. Like all data science projects, all start with clients, variables, and the relationship between them. We then usually run a propensity score, a pre-trained propensity score, which goal is to identify the probability of each client do something, okay? Churn, sell, whatever. We then sort the customers by that score and divide them into percentiles from the highest score to the lowest. We decide the cutoff point. To the group that have the percentiles with the highest score, we perform a randomized control trial. We split them into groups. To one, we'll give the treatment. To the other, it's the control. And this assignment from the clients to the groups is random. And this little detail will make a lot of difference in the end. It's random. To the other group, we don't do anything. So now we are ready to run the campaign and wait for the results, cross fingers, and hope it went for the best. While we wait for the results, let's just make a quick reminder on randomized control trial. What we are trying to find in randomized control trial is the average treatment effect. To one group, we will give the treatment, in this case the pill, and to the other one we don't give anything. Then we observe the outcome, and we can calculate the average of success in each group. The average treatment effect is just the difference between these two averages. So now that we know how to calculate the effect of the campaign, the results came back and we calculate them for our campaign. We get the average treatment effect. The biggest this value is, the greater the campaign went, and everyone is very happy, we'll get a raise, and we stay all very happy. And we can wonder, was this because of the campaign? And here we can say yes, because the clients were assigned randomly to treatment and control. And this little detail, in theory, eliminates the effect of any potential variables that could impact the result. And now you may wonder, then if we can answer this question, the impact was because of the campaign, why do we need more complex models? To look smarter, to get a raise? Also that, but the problem, in fact, is a little bit more complicated. Because, let's just resume our conclusions about this approach. If we imagine our campaign was to send an email to our clients to make them use our app, okay? What can we conclude about it? From the propensity model, we can conclude that one specific client has some probability of signing up. For example, Miguel has a 70% probability of signing up our app. Okay, that's good. From the randomized controlled trial, we conclude that the campaign in average have an impact of 5 percentage points. That is also good. But can we do better? Because what was really, really good is to know what was the effect of the campaign on Miguel, not across all the group. Because if we knew that, we could perform better. So what we really want to be able to say is emailing Miguel, in this case, will increase in 10 percentage points his chance of signing up our app. If we can do this, we can do this, which is classifying our clients in 4 different groups. We have the persuadables, that are clients or customers who will sign up if they are targeted. We have the sure things and the lost cases, that are customers who will or will not sign up whether they are targeted or not. They are not sensitive to the campaign. And we have the sleeping dogs, who are clients who will not sign up if targeted. Okay, we are especially interested on persuadables and on sleeping dogs because those are the ones who are sensitive to the campaign. So now we have a problem. How can we see the effect of the campaign in each client? That's a good question. Well, if we could observe parallel universes, we could see the client in both treatment and control. But sadly, our finance department didn't approve our request for a portal gun, so we have a problem. How do we solve it? Well, we have specialists like Miguel that knows a lot of math, and we will use it. Because we are handling with the fundamental problem of causal inference. It's impossible to simultaneously observe the outcome and the treatment in the single client at the same time. So right now, what we need to estimate is the conditional average treatment effect. It's different from the other one I show you because it's at client level. And it's conditional because it takes into account the individual characteristics of each client. The logic is the same, but it's at the client level. And usually it's also called uplift score. You'll listen Miguel talk much about uplift score. So some math, finally. How can we formalize this? Well, the conditional average treatment effect is the difference between the expected outcome under treatment and the expected outcome under control, given the individual characteristics. Okay, we have math, we have expected values. This really sounds like statistical stuff, so we need a specialist to talk about it. It's not me, it's him, so.
Okay, so thank you, Anna, for introducing to our current approach and also the problem that we are facing. So how can we solve this problem? So to solve this problem, we introduce something that we call uplift models. And they are different from traditional machine learning models. These are causal models, and they are designed to estimate this causal effect by estimating what would have happened in both control and treatment scenarios. There are several uplift models. The most common ones are the meta-learners, the ST and X learner, and why meta? Because we can use any type of machine learning model in each one of them. And we will also explore the double machine learning. That is a more advanced approach that takes into account some of the limitations of these meta-learners. So first of all, let's look at the overview of the meta-learners. As I said, meta-learners are designed to estimate the uplift score. And what is this uplift score? As Anna already explained, is the expected outcome under treatment minus the expected outcome under no treatment, or by other words, the probability of conversion under treatment minus the probability of conversion under no treatment. And how can we estimate these probabilities? Using machine learning models. We estimate these two probabilities, we make the difference, and we obtain this uplift score. But of course, this is only the overview, so let's look on how each one of the meta-learners works. The first one is the S learner. And why S? S stands for single. Single because we only use one machine learning model to train. So first, we train this model, and as input features, we give the covariates and also the treatment indicator, and as target is the outcome, because we want to estimate the probability of conversion. So here, first, for each new observation, we will estimate the probability of conversion under treatment and the probability of conversion under no treatment. Then, again, we make the difference between both, and we obtain the uplift score. This method has some advantages. It's simple, because we only use one machine learning model, and it's computationally efficient with small data sets, because we don't need to train one model for the treated data and another for the untreated data. But of course, there is also some disadvantages. This S-learner could be biased and can have weak performance and at high heterogeneity, meaning that if there is a lot of variation between features and outcomes for each group, this model can tend to underperform because it may be difficult to differentiate between two groups. The next learner is the T-learner. And why T? It stands for two, because we will use two machine learning models. So first, we split the trained data into the treated data and untreated data, and we treat one model on this treated data, and we call it treated model, and another model on the untreated data, and we can call it untreated model. Then for a new observation or a new individual, we predict the probability of conversion under treatment, and using the treated model, and of course, using the untreated model, predict the probability of conversion under no treatment. Then it's the same. We subtract one from the other, and we obtain this uplift score. This model has also some advantages. It's flexible and works better for large data sets, because we are training separate models in the treated and untreated data, and it helps us distinguish or get some different features and the relations between features and outcomes for each group. But of course, there is also some disadvantages. There is the risk of inconsistency, because if one model fits way better than the other, it can lead us to unreliable uplift estimates, and it can also be inefficient with small data sets, especially when the groups are unbalanced, and since one group can have less observations than the other, it can lead to overfitting. So let's just stop here. I just explained to you the S and T learner, and these are the simplest approaches. Now I will explain to you the X learner. It's a little bit more difficult to understand, so I break it down into 5 steps, so it's easier for me to explain and also for you to understand. The first one, it's equal to the T-learner. So first, we split the data into the treated data and untreated data. We treat our model on the treated data and another one on the untreated data. The second step is the imputation of counterfactual outcomes. And just a note here, from now on, the upper branch will be the treated data and the other one will be the untreated data. So what this means, the imputation of counterfactual outcomes? This means that, for example, for the treated individuals, we will use the untreated model to predict what would have happened if they hadn't received the treatment. And for the untreated individuals, it's the same. So we take the treated model to predict what would have happened if they had received the treatment. Then, in the third step, we calculate what we call the imputed treatment effects. So for the treated data, they are given by the difference between the observed outcome minus the predicted counterfactual, and for the untreated data is the predicted counterfactual minus the observed outcome. And still in this step, we train another 2 models for the treated data and untreated data to predict these new imputed treatment effects for each new observation. Then we estimate the propensity scores, but these propensity scores are different from the ones that Anna explained in the beginning. These are the propensity scores to be treated, meaning that we will train a model to predict the probability to be treated based on the characteristics of each client. And then we take all the estimations from these 3 models, we combine these estimations, we obtain this final uplift score. And this combination allows us to have a more accurate uplift estimation, because we are balancing for those clients that are more likely to be treated and those that are less likely to be treated. This is the overview of the X-learner. Of course, if I had shown you this in the beginning, it will be difficult for you to understand and also for me to explain. So in 5 steps, it's easier. This X-learner has some advantage. It's good at handling imbalanced groups, because we are balancing the propensity to be treated using these propensity scores. And there is also the model flexibility, because we can do several model selections for each one of the models that we are using. But of course, since we are using so much model, it adds a layer of complexity in this implementation, and also an increased computational cost, because more modeling steps and also more modeling tuning. So looking at these meta-learners in practice, we used a package called Causal ML that was developed by Microsoft, and as any other machine learning method, so first we initiate the models. For example, in the S-learner, we just have to pass the machine learning model that we will use to estimate the probabilities, And in the X-learner, we have to pass more models. For example, in the step 1, we need the same as the T-learner. Then we need another 2 to estimate the imputed treatment effects, and another 1 to predict the probability of being treated. So I already explained to you these 3 models, so take some time to really assimilate this information while Anna introduces to another concept.
No one leave the room, so good job. So let's just make a quick stop on the models, and it's the time to let you know about a crucial concept, that is confounder variables. In the perfect world, we would have treatment, outcome, and variables that could impact outcome. But as we all know, we don't live in the perfect world, we live in the real one. And sometimes those variables also impact on treatment. And when that happens, we call them confounders. So confounder is a variable that impacts both treatments and outcome, causing a spurious association. And this must be addressed, because if it doesn't, it may lead you to wrong conclusions. Okay? Even in our days, there are several peer-reviewed scientific papers that have this kind of problem in the data, and the conclusions have a bias. So it's not good, and we should be aware of this situation. We just have here one more simple and funny example. Imagine you have ice cream sales and sunburns, and you only have these 2 variables under your data, and the behavior between them is very similar. And someone that is not in this conference and don't know anything about causality may be wondering, wow, maybe ice cream sales cause sunburn. Obviously that is not true. But this is different from our first example, because in our first example, the relation between the variables was a coincidence. Here, it's not a coincidence. We have a third variable that it's not on the data, but that one really causes the ice cream sales increase and the increase in the number of sunburns. And that cause makes these 2 variables related, but one doesn't cause the other. And that is very important. That is why we are always saying, look beyond the data. Don't look just at the data, because there could be any kind of information that you are not looking for and that make bias in your conclusions. Now that we know what are confounders, let's hear Miguel again about how to deal with them.
Okay, thank you, Anna, for introducing us to this concept. And now to try to deal with this problem, we have the double machine learning, where double comes from 2 stages of estimation process, where we not only estimate the uplift, but also tries to deal with these complexities by reducing bias from confounders and handling high-dimensional data more effectively. And how this works? So in the first stage, we first estimate the expected outcome. So we train a model to predict the probability of conversion given the characteristics of the client, whether he was treated or not. And then we estimate the treatment probability. It's the same as the X-learner, is the propensity to be treated. So we train a model to predict the probability of an individual to be treated based on their characteristics, or given their characteristics. And in stage 2, we calculate the residuals, that basically are the predicted values, are the difference between the predicted values and the observed values. So in the outcome residual is the difference between the observed outcome minus the predicted outcome, or the predicted probability of conversion. And in the treatment residual is the difference between the treatment indicator minus the predicted probability of being treated. Then we just have to regress these outcome residuals on the treatment residuals and minimize the residual sum of squares to obtain an accurate uplift estimation. But here we still have a problem, and to explain to you this problem, let's see how things are supposed to work in theory. So first, we split randomly the data into the treatment and the control, and supposedly every client that was assigned to the treatment will be treated, and every client that was assigned to the control will not be treated. But this is the perfect scenario, and sometimes things doesn't always go as we planned. So in those cases, there can be the case where not all individuals that were assigned to the treatment may end up actually receiving it. And there could be several reasons for this. For example, in a direct marketing campaign, we have an operator that is calling the individuals that were assigned to the treatment, but for some reasons or factors that we can't control for, he may end up only calling some of them. And we call these factors unobserved confounders. So they affect the treatment, but we can't control for them. And at this point, we have these new two groups, the new treatment and the new control. The new treatment are the clients that are actually treated or were actually treated, and the new control, so they are the clients that were initially assigned to the control group, plus the ones that were not treated. And to summarize, we have these two scenarios. The scenario of perfect compliance, where all clients that were assigned to the treatment will actually receiving it, and the scenario of non-perfect compliance, where not all individuals that were assigned to the treatment may end up actually receiving it. So we need a way to try to deal with this problem. In the case, again, of the perfect compliance, there could be factors that affect the outcome, but will never affect the treatment or the treatment assignment. And in the case of non-perfect compliance, these unobserved confounders can affect both the outcome and also the true treatment assignment. And this creates a challenge in isolating the part of the treatment effect that we care from these unobserved variables. So to deal with this, we introduce a new variable that is the instrumental variable. And what is this? It's a variable that only affects or causes the outcome through the true treatment or through the actual treatment. And this variable will help us better understand the part of the treatment effect that we really care about, that is the causal impact of the treatment on the outcome. So now that I've introduced you to this variable, we need a model that deals with it. And I promise that this will be the last model, so bear with me just a few more minutes. This model is the double machine learning with an instrumental variable. And it helps us correct for scenarios where the true treatment doesn't always match the randomly assigned treatment. And by utilizing this instrumental variable, we ensure a more accurate uplift estimation because we can isolate the part of the treatment that is not affected by these confounders. And how this works, it's almost the same as the previous model that I explained. So first, we have a function to predict the probability of conversion given the characteristics of the clients, and also a function to predict the probability of being treated given the characteristics or covariates of the clients. But here we introduce another function that is also to predict the probability of being treated, but not only given the characteristics, but also this new variable, this new instrumental variable. Then we use the estimation from this function, we subtract the estimation from the old function to predict the probability, and we obtain this new treatment residual. Then it's the same. We just have to regress the outcome residual on this new treatment residual and minimize the residual sum of squares, and we obtain an accurate uplift estimation. So that's enough of models for today. And talk us about our use case. I think that's why they are here today.
Yeah, we just like to make you suffer a little bit. So now, finally, we get our use case. So we want to give you all the tools you will need if you want to implement this kind of approach. And that is why, until now, we didn't deep dive in any example. Now you have the tools to get what we have done. So we choose our churn in health insurance, our campaigns to avoid churn in health insurance. And let's see how we've done it. So we identify the propensity to churn clients, like in all other cases. And then, well, we needed to have data to train our uplift model, all the models Miguel has been talking about. So how did we obtain the data to train our uplift model? Well, we pick up our propense clients, we divide them randomly into treatment and control. And why we made this? Because we want to eliminate as many confounder variables as possible. And making this assignment randomly guarantees that. Then, to the treatment group, we made a phone call. We had a team of operators that are specialists in health insurance. So they called our clients, and they tried to figure out why the client is propense to churn. Maybe because the price is too high, maybe because the coverages doesn't match their needs anymore, and the operator tried to make an offer or propose that avoid the churn. We collect the results from the campaign and we join to the original data set. So originally we had the clients, the variables about the clients, and now we can join the information about the client is treated or not, and the information about the outcome. Did he may churn or not? And this will be the data set where we are going to train our uplift model. We then divide this data set into train and test. We train the uplift model in the train. We estimate the uplift scores, and we validate the model with the metrics, the more theoretical metrics. Then we segment the clients in persuadable and sleeping dogs. These are the ones we want to target, the persuadable. And we validate the segments. Once again, we use also common sense and the business expertise to see if the segments make sense. This is where we are now, okay? We have promising result tests, as Miguel will show you, and our next step will be deploy the model and monitoring the results, okay? But to talk to us about our promising results, Miguel, once more.
Thank you for introducing us to our use case. And now that we've seen how the models works, let's see how these predictions translate into real-world outcomes, and also how can we segment the clients into the persuadables and sleeping dogs. So in our case, we consider the persuadables as the top 30% of observations with the highest predicted uplift scores. And the sleeping dogs has the bottom 30% of observations with the lowest uplift scores. Here, we have a table that only represents churn rates. So just a note, these are the results from our test data. As Hannah said, we don't have the model still in production. And imagine if we applied the models and get the prediction, and segment the clients into the persuadables and sleeping dogs, and treat some of them, and while others don't, we would have, for the first model, the double machine learning, for the treated persuadables, a churn rate of 9%, while for the control persuadables, a churn rate of 9.6%. For the second model, the double machine learning model with an instrumental variable, for the treated persuadables, we would have the churn rate of about 8%, and for the non-treated persuadables, a churn rate of 16%. Then, so this shows that for both models, doing an intervention on these clients was the better choice, but the second model was better at distinguishing between control and treated persuadables. Again, for the first model, for the non-treated sleeping dogs, we had a churn rate of 17%, and for the treated sleeping dogs, a churn rate of 23%. Then for the second one, we had a churn rate for the non-treated sleeping dogs of 7.5%, while for the treated sleeping dogs, a churn rate of 18.5%. And this also shows that in both models, since we are talking about sleeping dogs, not doing an intervention was the best choice since it reduced churn rates. And again, the second model was better in distinguishing between treated and non-treated. When comparing between both, we can see that generally the double machine learning with an instrumental variable performed better, and we can compare these in the treated persuadables and the non-treated sleeping dogs. And why this? Because we want to treat the persuadables, since they are the clients that will benefit more from an intervention, and we don't want to treat the sleeping dogs because it may have a negative effect. But to make sure that this model is really good, we have to compare it to the baseline. And our churn rates from our baseline in the treatment was 13%, and in the control was 14%. And we noticed that for our treated persuadables was lower for about 4 percentage points against the treatment baseline, and for the non-treated persuadables, the churn rate was higher than the control baseline. And this shows that the model correctly identified the persuadables because doing an intervention on these clients led to a really lower churn rate when comparing to the baseline treatment. And for the sleeping dogs, for the treated sleeping dogs, the churn rate was higher than the baseline treatment, and for the non-treated sleeping dogs was lower than the baseline control group. And this also shows that the model correctly identified the sleeping dogs, and that not doing an intervention on these clients led to a lower churn rate when comparing to the control baseline. So these are the results from our test data. Now Anna will tell us about the next steps to put this model into production.
Well, after deploying the model, and almost as important as having a model is monitoring the model. No? So what are our plans to do it? Propensed clients are always the base. We'll divide them in 2 groups. For one, we'll perform the current approach. This will be our baseline to compare with the model results. And to the other group, we are applying our uplift model, the double machine learning with the instrumental variable. To the current approach, like I explained in the beginning, there are 2 groups, the treatment and the control. Everything will keep the same. Treatment, success, control, success. Then in the uplift part, we only want to treat the persuadables, and the sleeping dogs we will identify, but we won't do anything. What we are expecting to see based on the results in the test sample is we will have less calls in the part of the uplift model because we are only going to call to the persuadables and not to all the treatment group. But we are expecting to have more success on this sample because we are targeting just the ones who are sensitive to the campaign. On the other hand, in the sleeping dogs, we are expecting to have more success because they are not going to receive a call. In the upper part, the current approach, some of the sleeping dogs were in the treatment group because it was randomly. So we are expecting to have more success because they are identified and they will not receive a phone call. So, conclusion. What can we conclude about uplift models? They will lead us to less calls and a higher retention, and that leads to optimize our budget, okay? We all spend millions in marketing campaigns, and we think we could optimize that money to get a better performance, the good would be. So, to our main question about is it worth it? It was the theme of our presentation. We can say yes, okay, it's good. At least we hope so at this point. So, we leave here our LinkedIn contacts if you need to reach us. We really believe in the power of collaboration, so feel free to call us, to contact with us through LinkedIn. If you go next week to the office and you want to apply any of these methodologies at your problems and you don't know how to start, or if you have any doubts on your path, please feel free to contact with us. Thank you.
Thank you.